I'll go ahead and get started. So my name is Alex Gatch. I just finished my master's at Purdue University in Indiana. And now I'm back here in New York. I'm working for the U.S. Fish and Wildlife as a biologist, but I thought it would be pertinent to share some of the stuff that I did in Lake Huron because we're seeing some of these same issues in Lake Ontario. So it's kind of a good chance to get to connect with managers here in Ontario and see if we can implement these same kind of things. So we're going to be talking about restoration of spawning habitat, and I worked with Ed Roseman at the USGS, and I also worked with Thomas Hook, who is my advisor at Purdue University. So just a quick thank you to both of them, Thomas and Ed, and all of my funding came through the USGS and through Purdue University as well. So to get right into it, we all know spawning habitat is important for reproduction in early life stages, so that's critical life stage of fish. One example of this spawning habitat is rocky reef habitat, and these are used by lithophilic spawning fish or fish that use rocky substrates to spawn over. So some examples from our native fish are fish like lake trout, the carrageenans like whitefish and cisco, and also walleye. And the important part of these structures are the interstitial spaces, and these are the spaces created by the overlapping of those rocks within the structure, and they create these protective microhabitats for larval fish and also for incubating embryos as well. Unfortunately though, these types of spawning habitats are susceptible to both anthropogenic and some natural causes of degradation. So if you listen to Brian Lantry this morning, he was talking about some land use changes, some deforestation in the Great Lakes. So that's a great example of changes in how water flows through the terrestrial environment into the aquatic environment, and we can get some sedimentation within those interstitial spaces. We also have some more point source kind of things like dredging and channelization, where we're moving some of those sediments from one area to the next. We also have introduction of some non-native species like drosselid mussels, some benthic algae like Calafra that clog those interstitial spaces. They can also use some of that dissolved oxygen that the embryos require. And then we have our natural processes, right, like sediment resuspension from wave and wind energy, which transport sediments from certain areas of the lake. They can redeposit those sediments on top of our spawning habitats. So the combination of those anthropogenic and natural sources kind of led to some destruction or some loss of historic spawning spots in the Great Lakes. And so why is this a problem? Well, sediment deposition, shameless plug for a publication, has been shown to cause some negative effects on embryonic development and hatching success. So if we have reductions in early life survival, this can lead to impacts in year class strength. So to give you a simple example, if you have these clean interstitial spaces, those eggs have better hatching success, they result in larval fish, and then those fish can recruit to the adult population. But if you add things like sedimentation or different biofouling, you have degradation of these habitats, you have reductions in hatching success, which can lead to reductions in that wild population or that adult population. So right now what we're doing to kind of combat this is we're creating constructed reefs or augmenting or adding material to existing reefs. And this has been going on for quite some time, so since about the 1980s. There's a handful in each lake. And this is an example of a reef that was just built in Saginaw Bay, Lake Huron this past summer. So managers barge limestone or cobble out to the lake. They then dump it off the side of the boat, and you can see these 3D models of what they look like once they're formed. And these constructed reefs are in all of the Great Lakes. There are 3 here in Ontario. They go all the way from the St. Lawrence up into Lake Superior. But are these the best option? So initially, these structures are free of any type of degradation, right? They have great interstitial spaces, but the issue is that they can be costly. So for example, that reef right there costs about $1 million for 2 acres of habitat. But the main issue is that they're still susceptible down the line. So after 10 years, they can still have infilling from sediments. If we have another invasive species, like something like a clogger mussel that we haven't had yet, they can colonize those structures as well. So kind of the objective of my thesis at Purdue was to think of an alternative approach. Instead of constructing reefs, how can we better restore reefs that could be natural or that are constructed? So we thought of using some sort of routine maintenance or some kind of custodial maintenance on top of these reefs. And so this has been talked about for quite some time, but it hasn't necessarily been done yet. So we had to start from kind of the ground and build up from there and see what other people were using to remove sediments in other fields. So it could go from anything like dredges to suction dredges to prop wash apparatuses to underwater fans. And so the three objectives of this thesis were to, one, create a device, and it had to be portable and affordable. So in Indiana, we're about 6 hours from our field sites, so we have to be able to transport this thing from Indiana up into Lake Huron, and it also has to be affordable, so something that's practical to use. We also wanted to determine if we could remove, or we could detect removable amounts of sediment, so is this thing working? And then we wanted to see a fish usage change. So if we clean off a section of the reef, are fish using that section more than the degraded, or does it not really matter to the fish? So in 2018, we created 2 different devices. This is the first device, which we call the propulsion sled. It's a benthic sled, so it's pulled over top of the reef, towed behind our vessel. It has 2 underwater fans, and they're tilted at a 30-degree angle. And so the idea was that when you suspend sediments, it creates a massive plume, right? You can't really control where those sediments go. But if we could attempt at least to direct those sediments once we suspended them to the outskirts of the reef where we're cleaning, that was the idea behind the fans and the angles that we had on those fans. So this thing cost about $3,500, and we powered it from a generator that was on the deck of our vessel. This is the second sled. You can see it's a lot lighter and it doesn't cost as much. That's because I built this one, and we'll talk about the implications of how well it worked down the line. But this one uses pressurized water. So again, we're towing this behind our boat, and the fire pump that supplies that pressurized water is on the deck of the boat. We tested this on a number of different sites, but I'm only going to talk about 2 because we had the best results at these sites. Number 1, and number 2, I don't have that much time. So these are both going to be in Saginaw Bay. They're in the inner bay, they're not in the outer bay. The first is North Island Reef, so picture here. This reef has clear interstitial spaces, there's sedimentation, there's some resetted mussels, but this is because it's in really shallow water, so it's only in 2 meters of depth, and there's ice scour in the wintertime, so it kind of cleans out those interstitial spaces by moving those rocks around. This is in comparison to another reef that we tried to clean, which is Corian Reef, where if you remember that picture I showed earlier where they built a new reef, this is where they built it ultimately. But it's a bit deeper, there's no ice scour, and you can see there's no interstitial spaces either. It's completely covered in sediments, and then there's some beds of resented mussels as well. Just to give you a quick how we did this out in the field, each reef we had different treatments. We had a control, we cleaned sections with our propulsion device and our hydrojet device. In 2018, we kind of treated it as our pilot year, so we didn't have any replications. But in 2019, we increased the replications. Though these sites, we cleaned 50-meter diameter plots, which one of the reefs wasn't really that big, so we were kind of limited to how many replications we could have just based off the size of these plots. But they were circular, and we'd start from the inside and move our way out. And again, that was to try to push sediments from the inside of the reef while we were cleaning outside so they didn't just resettle back down. And then we did this for 30 minutes on each treatment. So if you look at our plotter, it starts off like that, and then by the end it gets kind of crazy as you pull out to the further. Here's a picture, so this is kind of what it looks like. We're just towing it right now. It's not actually on the reef, obviously. But we lower it down with our davit, then we hook it up to one of the cleats in the back with a tow rope that is like a kinetic energy tow rope. So if we were to get stuck on a rock or a boulder, it would give us some play, kind of like a rubber band before the boat just stopped and swamped the back of the deck, which never happened. And here's a video of what this looks like. So here's the propulsion sled. So this, remember, is the really heavy 200-pound sled, but it has these big fans on it. And if you're not familiar with Saginaw Bay, it's a very productive bay, very turbid, so it's really hard to get some good video here just because of the water quality. But so we're going to pull around here for a second before we turn on the fans. And this is chorion reef. That's that reef that doesn't have any interstitial spaces. But you start to see there's sediment mussels being suspended, maybe some benthic algae too, and sediments as well. So you can see where this thing is behind the boat based off the path of sediment plume that's coming up behind it, which makes it actually pretty easy to pull because you know exactly where it is. This is the backyard mechanic version of that, so you know it's probably not as good, but it uses pressurized water. Same thing, we're going to pull it before we turn it on. And then here comes the water. And so we would just do that for hours out in the bay. We try to clean off as much as we could, potentially clean off as much as we could. Okay. So the second objective, remember, was to see if we could kind of measure how much sediment we were removing, which is really hard to do. So we chose to use a proxy, which was relative hardness. So with side scan sonar, you can scan the bottom of the lake. There are different metrics that tell you how hard the substrate is. So if we were successful at cleaning sediments off the reef, we'd suspect it becomes more hard, right? There's more rock, there's more reef structure that's being scanned compared to sediments. So with that, we can use a software called Reef Master, which gives us these nice plots. You can calculate a mean relative hardness within a plot, and then compare pre-clean to post-clean. So here you see there's a lot of variation, and here there's a bit less variation, suggesting that you're cleaning some of that off, and you're just getting a harder reading back. We also looked at egg deposition, so are the fish using these areas anymore if you clean them off compared to the controls? So we set egg mats in 2018 in the fall, and the fall of 2019 for lake whitefish, and in the spring of 2019 for walleye. We'll start with North Island Reef. So shallow reef, clean interstitial spaces before cleaning. And so this is going to be a plot of relative hardness on the axis of the treatments, and so these panels are each sampling period as well. And then we looked at percent change in relative hardness. So if everything went to plan, what you'd expect is after cleaning, you'd have a data point in here like this one up here, right? Because you remove more sediment, your change is going positive, so that's good. So in 2018, our propulsion device did a really good job, it seems, in removing sediments, at least on the plots that we cleaned off. Our hydrojet sled actually decreased relative hardness, suggesting maybe we suspended sediments, but then they came right back down on top, and maybe even more than we had there originally came back on top of the reef. Control kind of stayed the same, that's good. In the next year, similar trends, the propulsion device again increases relative hardness. And this time the hydrojet does too. Not really sure what the difference was between these 2 years, but maybe it had something to do with the water pressure. This is also only increased replication, so this is a mean with one standard error around it. And then fall of 2019, so just a couple months ago when I was doing this, similar trend again, propulsion device increases relative hardness, while the hydrojet, we don't really know what it's doing. Sometimes it increases, sometimes it decreases. It's probably just not as good as a device, but the controls are always consistent, so that's good. So there you go, propulsion consistently. And as you look across sampling periods, you would suspect if you keep cleaning things off, you're gonna have less and less change over time because there's simply less material to remove. So that may also be happening as well. We look at egg deposition, so same type of plot here, treatment on the X. The Y is egg deposition in meters squared per day. We see this kind of matching of when you clean off areas of reef, you have significantly greater egg deposition in those areas. So we're potentially creating these higher quality habitats that either the fish select for or the interstitial spaces collect eggs better because it's a passive mechanism. So those eggs may just be getting stuck in interstitial spaces where the surrounding area is still covered with sediments. So we see kind of that matching there, which is good. And then chorion happens, which is not good. There's a lot of sediment. In some areas, there's up to about 1 meter of sediments. So we knew right off the bat that we probably aren't going to be able to remove any of those. And the relative hardness data suggests just that. There's really no change from pre to post-clean, and even among year sampling periods here. It's pretty much flatlined. We didn't do anything out there. And then the egg patterns pretty much match that, except for this outlier here. We saw a significant increase in egg deposition in one of the propulsion treatments. So that, I can't really explain that, but this makes sense, right? We didn't change relative hardness. Why would we see differences in egg deposition in those treatments? So just to conclude here, our first objective, can we create these things? We did both of them for under $4,000. They were easily towable by our 21-foot vessel. We never got stuck. We didn't have a problem pulling these things. And we could transport them on the highway, which is nice. To determine if we could remove any sediments, it looks like on North Island Reef, consistently that propulsion device removed sediments or created a harder substrate. And on the hydrojet device, it was a bit more variable, right? So it depended on the sampling period, and maybe that's happening just because it's not working as well. There's not enough water pressure to either suspend the sediments or then remove them off the reef once they're suspended. And then on Corian, we didn't see any changes because there's just too much sediment. And then our third objective, again, was to see if there's any differences in egg deposition. On North Island, it kind of matched, or it exactly matched increases in relative hardness when we compare those plots. But the hydrojet, again, was variable, so it just could be that that's not working as well. And then on Corian, generally, except for that one outlier, there were no differences in egg deposition among those sampling sites. So just some final points. Routine maintenance may be an option. It shows that we were able to remove some sediments, we made some changes in egg deposition, or saw some changes in egg deposition, but it's going to depend on the structure. So we did this in lake systems, we didn't do this in any loadic systems, which is going to totally change how sediments are removed with currents. And then we also note that it has to do with magnitude of degradation. So you're not going to be able to use devices like these to clean off a meter of sediment unless you're out there for days, which is another possibility. There are also potentially this cheaper alternative reef creation. They didn't cost that much to make. It didn't take that much time to go out. So it is a possibility that instead of creating new reefs, you could clean off existing reefs or clean off those constructed reefs that you put out and years later become degraded. There's also this potential to scale up devices. So our goal is to make it portable and affordable, but we could do the opposite of that, make them really expensive and use some of our larger research vessels if we can get into these reef sites. And then we know that there's this further development needed for loadic systems or riverine systems because it's not very safe to be pulling benthic sleds in something like the Detroit River or the Niagara River. And finally, there's this growing interest in maintenance of reef structures. It's been a thought for a long time, but this is really one of the first processes to go out there and try to document this and publish these kind of things. So if anybody has any ideas, I'm open ears. We're all open ears, anyone that works on reefs. It's something new and it's exciting, so thank you very much.